So welcome back, everybody. I hope you had fun this week in solving these exercises. Today, what I'm going to do is go through all the exercises one by one. First, I will try to ask to some of you if you want to share your solution or your attempted solution or the problems that you have encountered. Don't be shy, even if you don't finish. It's good to hear what were the problems you found, and feel free to interact me while I will try to solve them together to ask more questions or clarifications. So let me go to the website. So I will try to look for the exercises here. Perfect. So the first thing, I hope that all of you install the software and using the Conda software, which is pretty convenient to install everything that is needed for this masterclass. And after creating the environment, you activate it and you install everything that is needed. So I will jump directly to the resources here. So the first thing that you should do is, you should have done already, is to download from our GitHub of this masterclass all the material that you need, which is a couple of things: a PDB file of our system, which is again a membrane receptor in together with the serotonin ligand, and the second is a trajectory created with the GROMACS molecular dynamics code. I don't know if you're familiar with it; it's pretty popular. And this trajectory is, if you visualize the trajectory using, for example, VMD, you might have noticed that is in some frames, this trajectory, the system is broken in different periodic cells, so it's kind of discontinuous in the coordinates, and this might be a problem when we do our analysis in PLUMED. After this lesson is concluded, we will upload the video to YouTube. At the same time, I will upload a notebook, a Python notebook with all the solution in the GitHub. So you will find all the solution that we are going to do together now. Okay, so the aim of this first class was to learn how to use Plume to analyze existing molecular dynamics trajectory. We are not running any MD. That will be done in future classes. Here we download this trajectory that I run for you, and we analyze in terms of calculating some observable of the system. And to do this, we need to prepare separate from the molecular dynamics code, a separate input file in a specific Plume syntax. And here I put it for you one example that we actually are not going to use. Is just to understand more or less what is the spirit. We have to define some actions, label them with a name, for example, the distance between two atoms, and then we can use this distance for many things. The simplest thing we can do is to print the value of the distance on every frame or every 10 frames of your molecular dynamics trajectory. Okay, so this is what we are going to do, and we start with exercise 1, which is very simple. What we want to do is to calculate the radius of gyration on the C alpha atoms of just the first 40 N-terminal residues of the receptor. This receptor is embedded in a membrane. You don't see it because I remove it from the trajectory, and the first 40 residues are like sticking out in the solvent, so they are pretty flexible. And we want to characterize all the conformation that are sampled by our MD simulation. So the first CV is the radius of gyration. The second CV is the distance between the first residue and residue 40. So in order to complete this exercise, you had to complete this Plumed input file and then use a post-processing tool, which is called Plume Driver, to analyze the trajectory that I provided to you. So if some of you want to share the solution or attempted solution, this is the moment to do it. Anybody? Don't be shy. This is the simplest one. Okay, maybe I can start, and then the next one you can show me how to do it. So what I will do is use a Python notebook to do all the solution of these exercises. I don't know if you are familiar with it, but basically I've prepared a directory. I downloaded, sorry, the GitHub repository, and I'm here, and we will do the exercise inside this directory. And I open a notebook which is incomplete. We will complete it together. So basically what I have here is a series of cells and with a series of Python instruction that I can run line by line or block by block. And this is one thing that you can do with a notebook, but you can do many other things like embed directly some figures, doing some analysis of the output and embed some figures directly in your notebook. And also you can use different commands, not just Python commands. You can use bash commands, execute directly the Plume driver tool without going outside from the notebook. So it's very convenient, and we will do everything here. So the first thing that we need to do here is import some Python libraries that we will use in the notebook. And it's plumed, it's matplotlib to prepare some figures, some basic commands to create directory or directories, change directories, and MD analysis, which is another library to analyze MD trajectories. So the first thing is we run this part of the code. And as you see here, you got this number, everything went fine. The second thing that we are going to do is set a working directory. So the idea is that, let me open the shell here. We set this one as the main directory, and we will create for each exercise a subdirectory called exercise 1, 2, 3, and 4. But we need to tell the notebook where we are going to work here. So I just pasted the directory here. And then we want to check. So the system now is changing the main directory into this one. We want to check actually that this is the current directory. And we can do it in two ways. One, we can use a bash command, which is called pwd. And the second, we can use a Python command, which is part of this OS library. So every time you want to execute a bash command, which is the same command you would execute in your terminal, you have to put an exclamation mark before the command. So let's do this. Okay, so I'm changing the directory to the main directory here, and then I'm printing out the current directory in two ways. One with a bash command, which is this output. The second with the Python instruction here. So the result is the same. We change the working directory into this one. Now, what we are going to do is complete this input file. So we want to calculate, let me make this bigger. We want to calculate the gyration radius of the first 40 and terminal residues just on the C alpha and the distance between residue 1 and 40. So the basic way to specify atoms in Plume is to give really an explicit list of atoms comma separated. So this can be very tedious if you have to put like 2,000 atoms here to do by hand. And so we will learn in the next exercise how to make this operation a bit automatic. So now we do this kind of manually. So there are different ways. Either you open the PDB file that you have in the data directory. So you have a PDB file, you can open it, and you can select the atom index, which is the second column here of the first 40 C alpha. So you see this can be quite boring to specify this manually. So we want to be a bit smarter and go back to the notebook. And what we do is use a bash command awk to select all the C alpha. So the first column we take from the PDB file, we analyze the third column for all the C alpha atoms for which the residue number is lower than 40. And then we print the second column, which is actually the index of the atoms. So we do this. This is a bash command, but this is, let's say, you can run in this Python environment if we put an exclamation mark before. So if you do this, you extract from the PDB file the atom indexes of the first 40 residues, and we just copy them. This is really stupid for later. So there is a second way in which you can execute bash command in these cells. And the way is to start this cell by this bash command, which make the entire cell here a bash cell. So now from this point on, every command that you write below, it's a bash command, but the result should be the same. The list of atoms should be the same. Then I also added current directory and pwd. This is the same thing that you can do, for example, here in your bash, echo current directory, pwd. So, but we do this in, sorry, here, we do this in this Python. As you can see, the list of atoms is the same. So this is very quick and dirty, and it's not that robust, because if you know the syntax of a PDB file is not really defined by columns, but is defined by fields, really by individual characters, starting from the first one at the beginning of the line. So you don't always have a fixed number of columns. Sometimes the atom index is very large, and then it's the column of the atom index is merged with the column of a residue type. So the number of columns might change. So it's not a very safe way to extract atom indexes. Another option, which is much safer, if you can just directly in Python go through the PDB file. And remembering the syntax of a PDB file, so you know that column 1 to 6, here a column means really one character is a column. So characters from 1 to 6 are always atom or heteroatom or something like this, an identifier. And then column 7 to 11 is always the serial number, and so on and so forth. So this is the definition of a PDB file. So we can use some string manipulation in Python to parse the PDB file, check that the first 6 are really an atom, and then we pick the serial number, the atom name, and the residue sequence number more precisely based on the position on the character position in the string. So if we do this and we print the list, you should have exactly, in this case, the same list as before. Okay? So these are 3 different ways, 2 in Bash and 1 in Python, to extract kind of manually the list of atoms we need. And then I copy this because we will need for the completing the input file. So what I've done here, I just copied from here the template input file, and this is a bash, again is a bash cell, so everything from this point on is bash. We create a directory for exercise 1, and we go inside exercise 1. At this point, we create the input file, plume.dat, using this syntax, cut to, so put in the plumed input file all this text until end of file. So here what we need to do is put the list of atoms, comma separated with no spaces. And then for the distance, we need just the first and the last. At this point, we have to print these 2 collective variables on the callvar file every step. So you need to follow this instruction and complete with the argument and with the stride. So let's see if I can do it without looking. So we print the 2 collective variables, so R and D, on a file called callvar, and every 1 time step. So this is to print out your quantities that you define here on the callvar file. So once we will run this cell in Python, you will create the Plume input file with this text. But at this point, we can do more. You can directly analyze the trajectory, and I just copy the driver command. So once I will do this, basically I will prepare the input file and immediately run the analysis. So, okay, yes, of course. The XTC file, now we are in this directory. So the XTC file is not here actually, but we have to specify the correct directory with relative paths. Perfect. So we have a problem here already. Let's have a look. So we have
do you need the ... before data since it's one directory out?
Sorry?
Do you need the dot since it's
Yes,
one
sorry,
directory?
we are in this. Now we will have another error because the directory is present. Okay, perfect. Thank you. Okay, so we were in this directory, exercise 1, so the path should be with respect to exercise 1. So we have to go back one directory data and select the XTC file. So once we do this, the Plume input file has been created because I checked already. So the directory has been created, exercise 1. Let me clear a bit the screen. So we go inside and we will see the Plume input file here that we have defined in the Python notebook, and also the output, which is this Colver file. Now here, Plume always give you a very informative log that tells you which version of Plume you are using, 2.7, which trajectory you are analyzing, and what and other information that might be useful. And then it makes like a summary of what you're calculating, the gyration radius of these atoms and the distance between these atoms, and then what you're printing. At the end, you have other information about how many frames you have analyzed and so on and so forth. Okay. So did you have problems since completing these exercises? Nobody?
I have a question here.
Yep.
I did that, but specifically to exercise 1, I see that in the DAT file, we need not specify a structure file. We are just specifying a trajectory file in our command line. So I was wondering, how is it determining the structure, since we are not passing any information for a structure file over here?
Okay, in this case, you don't need any information about the structure. It doesn't care if it's a protein or a list of ions or anything. The only thing that you need here is to specify the index of the, let's say, particles that you need to calculate to calculate this gyration and this distance. And these are ordered, let's say, according to the PDB and according to the XTC file. So you see that here it's just taking the coordinates of a fifth, the 22nd, and so on and so forth particle in the XTC file to calculate something. So there's no need to information about the structure or what it is that you simulated. For other collective variables, yes, you need it, and we will see later.
Oh, thank you.
You're welcome. Other questions? Okay. So let's go to the next cell. Now we have a Colver file. You can always keep, yes? No. So now what we are going to do, and I gave you a Jupyter notebook to learn how to do this. We will import the Colver file of this exercise into a data set. It's called a pandas data set, so that we can do additional analysis directly in Python. We don't go back to the bash. So just remember, every time you open a new cell, you will be in the main path that we set above. So I made a mistake already, so it's very common to lose track of where you are, at least for me. So now we are in the main directory, and if we want to read the Colver file, we have to specify exercise 1 Colver. So what we are going to do now is to complete this exercise is to plot the time series of the radius of gyration and of the distance. And we use the matplotlib library, which is produces very nice figures. So what we do is we import the Colver file and as this data set, which is convenient because you can access, for example, let's look at the Colver file with VI. What you have is just first line fields, so what is printed in the file, and its time, the radius of gyration, and the distance. Okay, and this is for you have one line for each MD frame. So let's go back here. So we can use the same labels here to plot create a plot of the time of the simulation or MD frame versus the radius of gyration, we call RG, and the same thing for the distance, and then we just make it pretty. So if we do this, what you will see directly in the notebook is a figure showing the time evolution of the radius of gyration and the distance. And you see, if you look at the register generation, this goes from very compact, pretty compact structure here to more extended conformation. This is expected because I told you that the system is very flexible, and also you can see this in the, if you plot the distance between the first and last residue that spans different from 18 more or less 16 angstrom to almost 100 angstrom. So remember that the unit of measure in Plume is always nanometers, so is 10 nanometers maximum. So this is just to show you how to read directly the callbar file produced by Plumed and into the Python notebook, and how to visualize time series of your collective variable. Now, there was a question in the tutorial here. I was asking, are these two collective variables providing both useful information, or they are quite correlated? If you want to answer to this question, we can plot, for example, one variable versus the other. If we do like this, you see that there is a kind of a high correlation between the register generation and the distance. When you have a large register generation, usually, not always, but usually you have a very large end-to-end distance. So if you want to characterize a very complex system in terms of just two collective variables, you don't want to choose these two collective variables to be extremely correlated. Otherwise, it's a waste of time, because only one would be enough to understand if this is extended or compact. This is not really the case here, because they are quite correlated, but there are some conformations that are extended in the radius of gyration, but the end-to-end distance can be both either small or large. That depends if, for example, the first and last residues in this extended conformation wrapped themselves close together or not. So they are correlated, but they might be useful both of them. So do you have questions regarding this exercise? No? Okay. Let's go to exercise 2. So what we've seen here is that to complete the input file of Plume, which is right here, you need to manually select the indexes of the atoms, which can be kind of a boring operation. So now in exercise 2, we learn how to do this in a more automatic way. And we have two examples. One, if we want to calculate a torsion, a dihedral angles, on a certain residue 2. So we want to calculate the dihedral phi. If you are not familiar with proteins, here you can see what is the definition of a dihedral angle. So it's this angle phi, which is defined by 4 atoms. One, so this is for residue 2. Imagine I is equal to 2. So to specify these 4 atoms, this dihedral, you need the C atoms of residue 1, and then the N, C alpha, and C atoms of residue 2. So this is one possibility. You look at your PDB file and you write down the atom index, these 4 atom indexes. But in Plumed, there is a second way to do it. And now we need to learn what is the structure and the topology of the system. So we need to provide a PDB file here and use this directive, which is called, this action, which is called molinfo. So it reads some information about the molecule, and we need to specify it from where. So we need to put a PDB file here. And then in this exercise, we want to specify this torsional angle phi of residue 2 in 2 ways, which are equivalent if you do things correctly. One is you specify the 4 atoms that I just showed you, the red atoms. And the second way, we use a shortcut, which is provided by molinfo. If you don't know what are the possible shortcuts that you can use, you just click the molinfo, and you will see all the things that you can select automatically. For example, all the water atoms in your system, or all the ions. There are some special keywords that are activated once you specify molinfo. If you scroll down, you will see, for example, here, that you can select the atoms defining the psi torsion of residue 1 simply using this syntax. Or if you scroll down again, now we are interested in phi, you can specify these atoms with this syntax, at phi dash 2, because we want the residue number 2. So now we can complete easily our exercise. First, we do things manually. So we don't look at the PDB, we use this awk command again to select manually from the PDB file. So it's here from the PDB. We select the C of residue 1 and the N, C alpha and C of residue 2. Okay, so these are the atom indexes. You can do this manually if you open the PDB file and look. Now we have 4 atoms, and you can do it manually. Once we do this, we have to complete again the input file. So which I pasted here in this cell. We create, it's a bash again cell, so we can use bash command. We create a second directory, exercise 2, and we enter this directory. And we will have 2 sub exercises. So this is the first one, A. We need to activate the molinfo functionalities with this command. And now the path luckily is set correctly to data and the PDB. And then the first way to define the torsion phi of residue 2 is an explicit list of 4 atoms, which are this one. So I will put here the 4 atoms. The second way of defining this torsional angle is out in an automatic way, let's say, and we learn that is phi of residue 2. Now, what we want to do is to print on the file called corvar the 2 torsion, which should be identical every one step. So here you see, thanks to this cat command, we will put all of these in a plume_a.dat input file until the end of file, and then we will execute the driver on the trajectory. Do you have any questions? Okay, let's do this. So this is pretty quick. We can scroll down the log file, and here, when you use automatic selection, let's say molinfo selection, you will always see in the log file what are the atoms that have been selected. So already at this point, you can check that the first definition of a torsion is identical to the second definition of a torsion. The advantage is that I didn't search for these atom indexes in the PDB file. Okay, now, if you didn't notice this, we can check that the 2 variables are, let's say, identical, visualizing them or printing them on this notebook. So what we do, as we did before, we import the corvar file, which is now in exercise 2, as a pandas dataset, and we print it. Just we really look at the number. And the second thing that we do is to plot the time series of the difference between the 2 collective variables. Alternatively, you can plot 2 time series of T1 and T2, and so it's just the beginning. And if you scroll down, you will have the time series of all the 2000 frames of the difference between the 2 collective variables. So you see that they are identical. And so this selection using molinfo is really working properly. Okay, so this was the first part of the exercise. All of you managed to run this, to complete this correctly, or some of you had problems? Don't be shy. Okay, I assume that all of you completed this part of the exercise. So the second one is a bit more advanced. So let's go again to the, let's go to the, let's go back to the instruction here. So the second part of this exercise the aim is to learn more advanced selection tools, and to do this we need to have installed the MD analysis or mdtraj or both libraries, and we did this with the conda at the beginning. So these are other Python libraries that allows you to manipulate PDBs or to analyze trajectories. So, and they have a set of selection tools that are very advanced. So we linked with these libraries so we can use their syntax to select atoms. So what we are going to do in this second exercise 2B, let's say, is to recalculate again the radius of gyration and the distance on the first 40 C alpha atoms, but this time we don't put a long list of atoms, we select them automatically with either MD analysis syntax or mdtraj syntax. We actually do both, and then we check that the time series again is the same. So what I did is copy this part to the notebook here, and now if I remember how to do it, we need to complete it. So this is MD analysis. We have to specify the residue range, which should be like this, and the name of the atom, which is C alpha. So you see this is all in parentheses because it's interpreted in terms of the MD analysis library. And then here we have just residue 1 and 40, and again we have C alpha. And if you don't know the syntax of MD analysis, you can there is a link on our material to the manual of these libraries, and then you can learn the syntax, but it's pretty easy. The only thing that is different, the syntax between these two libraries. So this is for MD analysis. For mdtraj, if I remember correctly, the residue, the SAD starts from 0. So we have to do this, and the name is always C alpha. So here is 0 and 39, and the name is C alpha. And again, we need to print on file colvar. Now we have 4 corrective variables: the radius of gyration and the distance according to MD analysis, and the radius of the gyration and the distance according to mdtraj. And we print this every 1 frame. Okay, now this should be correct. We will, no, there's something missing here. We have to specify the PDB file. Now I'm lazy, so I will copy it from here. Here we go. So all this will be put in a plumed underscore, sorry, except end of file. All this will be put in plumed underscore b.dat. We load the PDB, we select, and we print. And then we calculate, we use the Plume driver with this PDB file, with this input file on the trajectory. Here we go. This can take a little bit longer. Okay. You can check that everything again is correct if we look at how our selection, so this is the first selection, which is sent to MD analysis, and then MD analysis select based on the syntax these atoms. So you can already check that these are the same atoms as the one we used before, and also this one. And this instead is mdtraj. So the selection is interpreted using mdtraj, and here is the atoms that are actually retrieved and used. And as you can see, they are the same. But if you don't look at this log file, we need to do something else to check that the trajectory are actually the same as before. So here we import 2 different datasets, 2 different pandas datasets. One is the previous exercise number 1, and we import in the data 1, and this one in data 2. And what we plot is the time series of the difference between the radius of gyration calculated by MD analysis, let's say, or using the atom selected by MD analysis, and the old one, and the same for mdtraj. So this difference should be 0. Now I marked this with a different thickness, so you can see maybe that they are both 0 along the trajectory. Okay, and the same thing we do with the distance collective variable. We don't need to import again the data set, they are there, and we just plot the difference between distance in MD analysis and the old one, distance in mdtraj and the old one. So if we do the same, here again, distance in MD analysis and mdtraj, the difference is constant and it's 0. So I have a question for you. Did you manage to, all of you, to complete this exercise?
Yes.
Some of you had problems. Nobody? Okay. Okay, we can go on to exercise number 3. So let's see. Okay, exercise number 3, it's about defining some virtual atoms. Virtual atoms are not actually atoms, but are virtual in the sense that they are defined in terms of the position of other atoms. For example, the center of mass of a group of atoms, of the geometric center, can be considered virtual atoms. We can define it somewhere in the plumed input file and then use it as it were an atom to define our collective variable. So in this exercise, we focus on the geometric center of a group of atoms, and we want to calculate the distance between the geometric center of serotonin, which is this molecule, and the geometric center of 2 glycans that are attached, they are polymers made of sugars that are attached to 2 residues of this flexible N-terminal. So if you look at the structure of the PDB of your system, you will see that attached at residue 24 and 32, there are some long polymer, and these are the 2 glycans. So what we want to do is to calculate the distance between the center of mass of the 2 glycans and of the serotonin. And so to do this operation, first we need to define the ligand atoms, then and the center of mass here, the center of the geometric center, there are no mass involved here, and then do the same thing with the 2 glycan. Then we calculate the distance between ligand and G1 and the distance between ligand and G2, and we print on the Colver file. So this is very easy. Hopefully you did it, you completed it. And I want to show you another way to specify atom indexes. So it's very convenient if your atom indexes are in sequence to specify as a range. So that's why I'm doing this explicitly. You could also use these MD analysis or mdtraj libraries to do this, but I want to show you another way, which is convenient when you have a range of atoms going from a minimum to a maximum, and you need all of them. So in this case, if you look at the PDB file, the serotonin is defined from this atom index to this atom index. So I don't remember if I've included the hydrogen or not, probably not. Let me check. It's up to you, you can do it differently. 6671. Yes, I excluded all the hydrogen. It's not really important, you can do with both. And then the 2 glycan are, if you look at the PDB file, they are not specified next to the residue they are attached. So the first glycan is attached to residue 24 and the second to residue 32. But actually, the glycan are specified, all of them, at the end, soon after the protein. Let me see how I can look at this. Okay, here we are. So the protein ends at residue 390. And then starting from this atom, 6212, you have the first glycan with this weird residue name. And this, I think, it's 9 residues. So if you scroll down, that's the end of the first glycan, 6424. Okay. And then the next one is the second glycan, 6425, up until the ligand here, 6658. Okay, so I put the right numbers here. This is one way to specify the atom. So it's just yet one more way. So perfect. Now we have a geometric center of this 3 group of atoms, and we can use them to calculate distances. Exactly like here, putting an atom index, 2 atom indexes, we can put 2 labels, provided that we have defined them before. And then, oh, this is incomplete. Then we have to print the 2 distances on a file called conval every one step. Okay. So again, this is a new exercise. We create the directory, we go inside, we create the Plume input file, and we run the driver. And this should work perfect. So if you have a look here, you will have in the log, it will put explicitly again the list of atoms that define the ligand and the two glycans. So you can double check that everything is done correctly. And then you will calculate the distances and so on and so forth. Okay. So now if you go back, did you manage to do this? Or you had problems? Okay. I assume no problems. So now there is a, sorry, if you write in the chat, I'm not sure please, it's a problem for me to keep track of a chat. Could you just switch on the microphone and ask questions, because otherwise I get lost. So now, so in the future, if you can please just switch on your microphone and ask your question. Thanks. Okay, so there is a question that we need to answer here. Let's now analyze the output of the calculation by plotting the time series of the two CVs. Can you say if the ligand is overall staying closer to the first or second glycan? So we can do that. Here. So we import the gain exercise 3, the Colvar file, and we plot the time series of D1 and D2. D1 is the distant glycan 1 and D2 glycan 2, and we plot this time series. And then we can do more than just watching this time series. We can calculate when the ligand is closer to G1 rather than D2. And to do this, we just go through the time series. So we do a Python loop, and we check if data D1, so the first distance, is lower than the second distance. If this is the case, we just increase this counter by 1. This is a very stupid way to do this calculation, but I think it's very clear. And then we print out the percentage of frames in which the ligand is closer to G1. So this is this count divided by the length of the trajectory. And this is percentage, so I'm multiplying by 100. So let's do this. Perfect. So you have the time series of the two distances, which to me is not that clear who is staying closer to the ligand, but luckily we have calculated automatically this this percentage of frames. So ligand is closer to G1 44% of the time. So actually it's G2 which is staying closer to the ligand for the majority of the simulation. So did you sorry, can anyone ask question on my behalf? I'm unable to do it because of network problem. How to define geometric center for residue rather than defining atom number? Well, sorry, I have to go back here. So here, when you have the definition of a center, okay, let me put the chat here. Maybe I can keep track. So here, when you have atoms, instead of let me say this, in PLUMED you almost always use atom indexes, but this is not a problem because the geometric center of residues, you just have to specify the atom indexes of all the residues that you have. And to do this, you can use the selection, the MD analysis or mdtraj selection. So you just select the residues that you are interested in. This will be automatically translated in a list of atoms, but always this collective variable works with atom indexes. Did I answer your question?
So that would be a res name LIG, for example, right? So just use the residue name of the ligand in the PDB to specify that.
Yes. So that, if I remember, let's say the syntax, it should be MD analysis, something like res name lig, something like this. I think we will use the syntax below, but so this is not needed anymore. So that can be done actually, but I didn't do here. I did it below because I wanted to show you how we can use ranges to select atoms. But this is certainly not the easiest way to do it. Other questions? Okay. So perfect. Now we check that the second glycan is closer to overall to the ligand than the first glycan. Very good. And we did this without basically exiting from this environment, this Python notebook. Now we are almost halfway, but now we have a more difficult exercises, which is number 4. Number 4 is about solving discontinuities in the trajectory due to this periodic boundary condition. Let me see if I can show you really what I'm talking about. So if we go in the data directory, so it's here, and we visualize the PDB together with the trajectory file, hopefully you can see what I'm talking about. So as you can see, the system is broken in different simulation cells, which is a periodic cell, so it's repeated in infinite number of times, and the system is just split here in these two, and then this is a small molecule, and this long bond, because these atoms actually are chemically linked, but so they should be very close, and they are very close. It's just they are visualized here in different simulation cells. And so this bond is longer than it is actually is. So I can scroll through the trajectory, and you see from time to time this conformation is broken in more pieces. Look at here. So to calculate some variables implemented in PLUMED, you need to account for the fact that the system is broken in this way. What we have done so far, let me close this. In what we have done so far, actually, we didn't need to do this. For example, here, for this center, this distance, automatically PLUMED is reconstructing the system in one simulation cell. And it used basically the indexes of the atoms to reconstruct, following the order in which these atoms are specified, and putting them one close to each other in the same simulation cell. But this is not true for all the variables, and there are some variables that requires that you reconstruct the system as a whole before calculating the variable. And there are 3 particular collective variables for which you need to do this, and these are called alpha RMSD, para beta RMSD, and anti-beta RMSD. These are secondary structure, let's say, collective variable that measure the amount of alpha helix, of parallel beta sheet, or anti-parallel beta sheet. And to do this, they compare the current frame of the trajectory with an ideal alpha helix or an ideal beta sheet, parallel and anti-parallel. And this comparison is done using the RMSD, root mean square displacement matrix. So before calculating this variable, you need to be sure that the part of the system that you are analyzing is not broken by periodic boundary condition. So you need to fix this, and there is a special action to do this, which is called all molecules. So if you click here, all molecules allow you to rebuild molecules that become split due to periodic boundary condition. And you need to specify, it's very simple, the list of atoms that you want to make whole with this keyword entity. So we go back here, and we need to complete this input file. Okay, exercise 4. Okay, I start to completing this already. We create again the directory, we go inside, and we create this input file. The first thing is we need to understand, you will see later why, we need to learn about the topology and the structure of the system. So we read, as we did before, a PDB file. Then we want to calculate the content of alpha helix and beta sheet of the first 40 residues. So we want this to be not broken by PBC. So the entity let's say that we are going to rebuild as a whole is just these first 40 residues. And I'm using the MD analysis syntax to select them, but you can do this manually. If I remember correctly, this is atom 12588 or something like this. But let's use, because we learned them, let's use these advanced selection tools.
I have a quick question here.
Sure.
So here, when we're using MD analysis, are we specifying protein as well as residue IDs, because we have other residues which are glycans with the same IDs?
Exactly. The problem is that in this PDB, the numeration, the residue number restart after the end of a protein and for the glycans. So if you select just residue 1 and 40, I'm pretty sure that you will select also some glycans. And for this case, we don't want them. We just want the protein itself. So that's why I put protein and residue 140.
Okay, thank you.
Thanks for the question. Once we have fixed the PBCs of at least of these first 40 residues, we can specify here. So now in this particular CV, you can use the residue numbering, the residue selection. So we put 140, 140, 140, and optimal is, I think it's not compulsory. It's the default action of flag is the way the RMSD is calculated. It means optimal alignment. So before calculating a difference in coordinates between two conformations, you have to align them optimally. So an optimal translation and rotation of the two conformations before calculating the difference. So this is needed, but I think it's the default one is optimal. What we needed to do is just to specify the residue range. Now, my question was, what is the total, the alpha helical content and the total beta sheet content? So these two variables, PB and AB, give you the parallel beta sheet content. So when the beta sheet are like this, and the anti-beta when they are anti-parallel. So we don't care if it's parallel or anti-parallel. We want just the overall amount of beta sheet. So what we want to do, what we can do, is to sum the value of PB and AB. So we define a new collective variable B by combining. This combine is just a sum. We can let's go here and check what is this combine. Combine can combine different collective variables using these functional forms, which is very simple. And you have to specify this parameter, this factor here, and the power here. If you don't specify anything, by default, you just sum the different collective variable. So this is a clear example. You can combine the X, Y, Z component of one distance to the power with the power of 2, and then you define basically a distance square. In our case, it's much simpler because we just sum two collective variables, so these powers need to be 1. And this, if you go down, this power is by default 1, and the coefficient is by default 1. So if we don't specify anything here, just PB and AB, what we are going to do is to sum the value of a parallel and anti-parallel beta sheet, so you have a total amount of beta sheet in your conformation. And finally, we want to print again on the file Colvar just the total, let's say the helix and the total beta sheet every one frame. Is it clear so far, this exercise? Okay. So we have prepared the input file, hopefully it's correct, and we do again our analysis using the driver. So this will take a while because these collective variables are pretty expensive to calculate, both during the simulation and after the simulation. So you see that here is still running. And once we will have the output here, we can proceed. Okay. Again, you can scroll and look that everything is correct. So here is residue 1 and 40. from 1 to 40 and the protein. So it goes from 1, if I remember correctly, yes, to 558. So clearly the glycans are not selected because they had a very large number. And then you have the alpha RMSD, the beta, para-beta RMSD, anti-beta RMSD, and then you combine parallel and anti-parallel with coefficient 1 and powers 1. So it's just the sum of the two variables, and you print out. Perfect. Now we want to analyze, and as usual, we import the Colvar file in a pandas dataset, and we plot the time series of the alpha helix content and the beta sheet content along the trajectory. And if you look at this, you can see that here you can think of as like the number of I don't remember if the number of residues that are the number of triplets of 6 residues that are in an alpha helix of beta, in an ideal alpha helix of beta sheet. I don't remember how many, but let's say the number is proportional by the length of the beta sheet of the length of the alpha helix. And if you have something like 0 or close to 0, it means you don't have alpha helix and you don't have beta sheet. Okay, this is kind of qualitative. What we can do to answer the question, it is more beta sheet or more alpha helix, we can first have a look of the plot of the alpha helix versus beta sheet content. So it's very simple because you have the quantity in the data set. So you can plot one against the other like this. And as you imagine, this is kind of an L-shape plot, because when you have a large amount, let's say on alpha helix, you cannot have beta sheet because it's one or the other. And when you have a huge content, large content of beta sheet, you don't have alpha helix. And then there is here some middle ground in which is probably not one or the other. So what I did, but it's let's say this is kind of personal. What you can do to define if it's beta sheet or alpha helix, I define if the beta sheet content is greater than 1, then I say that this conformation is a kind of a perfect beta sheet of some length. If the alpha helix is greater than 1, I'm saying that this is an alpha helix. This conformation is assigned as alpha helix of different length. So to understand if it's more alpha helix of beta sheet, the conformations, what I can do is again go through the time series of the CVs, and if the value of the alpha helix collective variable is greater than 1, then I increase this by 1. If the beta sheet is greater than 1, I increase this by 1. And then I'm just printing the percentage of alpha helix conformations and the percentage of beta sheet by dividing by the length of the simulation. So this is one possible way to do it. And if you do this, if you use this definition, you will see that on overall, the beta sheet beta sheet conformation are more populated than alpha helix conformation. This is one possible way to do it. Do you have questions on this exercise? Did you solve it in different ways? The quantification of if it's more alpha helix on beta sheet? No? Okay. Now, I would like to move to exercise 5, if there are no questions about this, this exercise. Okay, let's go back.
I maybe have one question again,
Yes.
how to interpret this. So if you read in the documentation, this S value, you're actually calculating in the... So is it correct that you are not specifically calculating a root mean squared deviation in the actual collective variable?
I'm calculating, let's say, inside the before defining the collective variable and calculating collective variable, I compare the current conformation to an ideal alpha helix using an RMSD matrix.
Yes, yes.
And then there is a sort of threshold. Is the RMSD is lower than something? I don't remember if it's a few angstrom, 1 angstrom, 2 angstrom. It's written in the manual. Then I define the conformation as alpha helix because it's closer than X angstrom to an ideal alpha helix. And the same for the beta sheet. And the actual number of a CV should quantify, if I remember correctly, the length of the alpha helix.
Okay, thank you.
Does it make sense? Other questions? Okay, now let's go to exercise 5. We have 3 more and they are more difficult. Exercise 5 is about gains using RMSD, which we touched a little bit before with the alpha helix and beta sheet. But now we want to really calculate the RMSD in two different RMSD. So we focused first on the very flexible and terminal part. And we want to calculate the root mean square deviation with respect to the reference conformation, which I included in the GitHub, once we align the protein only on the rest of a sequence. So we align, since these 40 residues are very flexible, to calculate the RMSD, we want to align, because we decide to do this, on the part of the protein which is pretty stable during the simulation. And so the RMSD in PLUMED, you can specify one set of atoms to use for this optimal alignment, and another set of atoms to calculate the displacement with respect to the reference conformation. And to do this, you have to define or specify an additional PDB file. If you look at the instruction for RMSD, in this PDB file, there is a way to use the PDB syntax to mark the atoms that you want to use for alignment and the atoms that you want to use for the displacement. And if you consulted the manual, you should have discovered that you can use the occupancy column of the PDB file, which is the last but one, to mark with 1 the atoms that you want to use for alignment and 0 the others. And to instead mark the atoms that you want to use for the displacement, you have to modify with 1 the B factor or temperature factor column, which is the last one usually. So in this way, you can create you create a new PDB file in which you mark which atoms you want to use for alignment or displacement. Once you've done this, the syntax of the RMSD is pretty easy. Let's go down. So we skip for 1 second here. So the syntax for the RMSD is pretty easy. You have a reference file in which you mark the atoms as I told you. And then again, you specified which type of RMSD, always an optimal alignment, rotation, and translation. And this is the 40 residue with alignment on the backbone of residue 41 to 390. And this is the backbone RMSD of 41 to 390 after aligning on the same atoms. So the syntax is very easy of the RMSD. The thing to do is to prepare these PDB files. And I want to ask you if some of you completed this exercise and want to show me how you did this. At least tell me if some of you if you had problems with these exercises or not, or all of you completed this exercise. Okay. Let's hear from people who had problems. Don't be shy.
I think the manual maybe could be a bit clearer. It takes some time reading into. I mean, there's a lot of text. It's no problem. You just read it. But actually, it could be nice to put it in bullet points. What you should put into occupancy and what you should put into the.
Okay. I understand. There are a lot of definition and formulas
that started out with scrolling down and see if I can find it in the, the bullet points here in the end.
I agree.
It actually took reading all of it to just find the definitions.
Okay.
Yeah.
I agree.
I couldn't complete this assignment because I didn't realize that we had to how to specify the reference atoms in the reference PDB file.
Okay.
So it's now when you are explaining it that I've realized that is how I was supposed to do it. So
the manual was not clear. Again, if you click the RMSD here, you couldn't understand how to specify the atoms for alignment and the atom for displacement. Okay, we should make this clearer. Other comments? Okay. Yeah. Yes. I hear something.
No, it was the same thing. It was just that it took me a while to find where how to do the ones and zeros.
Okay.
Yeah, so it was just a matter of like, I read the whole thing and then I'm like, oh yeah, there's actually a link here that I should click on. So.
Okay, let me switch on the light. And can I ask to people who actually did the exercise how they select the atoms, if they did this manually or they use some script?
I use VMD, the VMD command line.
Okay.
I did it manually using like a column editor where you can select one column of your text file and then edit it.
Good.
I used Python to read the PDB first, and then I changed the column values and I wrote it again, which took me some time. So I'm hoping that there's an easier way to do it.
There is. Okay. Other solution, creative solutions. Okay. So I did it in the past multiple times just by hand with VI or awk. So now I will show you something a bit more automatic. So since we have used MD analysis before, I'm showing you how to do it with MD analysis in this cell here. So as I told you, first we need to create two reference PDBs to use with the RMSD. The first one, we align on the backbone atoms of residue 41 to 390 and calculate on the first 40 residues, always the backbone. The second RMSD, alignment and displacement of the same atoms, which is the 41, 390. So what we can do is create what is called a universe in MD analysis. So we basically load the PDB file. And this is the same PDB file that I put in the GitHub. Then we go through all the atoms in the PDB and we first set occupancy and B factor, temporal factor to 0. So none of these so no atoms are used for alignment or displacement after this operation. Now we create two selections in MD analysis, one for the backbone atoms of residue 140. So this is the syntax. Again, I put protein here because of the glycans. So protein and backbone and resid 140. And then the second selection, which is protein and backbone and resid 41, 390. These are the two, let's say, selections that we will need for the rest. Now, what we do is the atoms that we use for alignment are always the same, which is the backbone of this 41, 390. So we basically cycle over these backbone atoms and we set the occupancy to 1 because these are the one that we use always for alignment. Then we prepare the first PDB. The first PDB we calculate the displacement of the first 40. So we cycle on this and we set the beta factor or temp factor to 1. At this point, we are ready with the first PDB because we mark the atoms correctly and we write down the first PDB. Then we need the second PDB. So we need to re-put back to 0 the displacement on the first 40 residues as it was before. And then we cycle on the, again, residue 41 to 390, and we put the beta factor to 1, the temp factor to 1. And then we print the second PDB. So this, I think, is pretty efficient, I hope. And basically, you don't manipulate your PDB by yourself. You just use MD analysis to set occupancy and temp factor after you have using these selections. So let's do it. You have some warning regarding the unit cell, which is basically not specified, but we don't care. We just have a look. So these are created in data. So ref1 and ref2, if you don't believe, you should always check. So ref1 should be displacement, so the last column set to 1 only for the backbone atoms of the first 40 residues. So this is N1, C alpha, and then you go down, C, O, N, and so on and so forth. And if you go to residue 41, kind of manually, you will see that at 41, you start putting 0 in the last column, and you start to mark as 1 the backbone atoms of these residues. 1, 1, 1, 1, 1, and you can scroll down until residue 390, and you will see that this is correct. So we believe also ref2 is good. Perfect. Now, once we do this, we have created the PDB file automatically. We can just put the path here. Hopefully, we are in exercise 1. PDB. Done. And then we print the two PDB, the two RMSD argument RMSD1, RMSD2 on file callbar. In one step. Okay, and we calculate the RMSD on the trajectory, so you can check. Probably it's not very easy to check by this log, and this should be done. Now what we want to understand is the fluctuation of this part of the protein during the simulation, so we can plot the time series of RMSD1 and RMSD2 using Matplotlib again, and you should have something like this, which means very large fluctuation of the first 40 and terminal residues, and a little bit more stable the rest of the protein. People who completed the exercise, you obtain something like this. Can you confirm?
Yes.
Yes.
Perfect. In these ranges. Okay. Question from the other people who did not finish the exercise? Okay. If you don't have questions, let's go back to exercise 6. Now, the last two are really more complicated. Okay, exercise 6 is about, is connected a bit with RMSD, what we have shown before, is about how to align a conformation during in MD trajectory during the MD simulation to a reference conformation before calculating some collective variable. So this in this specific case in which you have a membrane protein and a small molecule that is interacting with some part of the protein, what one would like to calculate in many cases the position of a small molecule with respect to the lipid bilayer. For example, if it stays outside, it goes inside the membrane, and at which point of the where inside the membrane. So, and many people want to use the coordinate, the absolute coordinate of for example, the center of mass of the ligand. And this is a bit problematic because if you imagine in the beginning, if you're familiar with the simulation of membrane proteins, you have a lipid bilayer which is parallel to the XY plane. This is almost always the case. And then you have your protein embedded in the bilayer. And the small molecule, then the position, the Z, the coordinate of a small molecule, is a good measure of how far you are from the membrane, because the membrane is parallel to the XY plane. So Z is a good measure. But during the simulation, you have these two problems. The system can translate from the original position, can go everywhere, and can be broken by periodic boundary conditions. So you cannot, without doing other things, other special operation, you cannot use an absolute position of a center of mass of a ligand to understand or to map where the ligand is with respect to the lipid bilayer. You need to do other operation to enable this. And the suggestion that I gave you are the following. The first thing, you have to be sure that there are no problem with the boundary condition in the protein. So this is reconstructed as a whole in the Plume input file. Then you want to check that the ligand is not broken by periodic boundary condition, and it's also in the same cell, periodic cell, let's say, as the protein, because you can reconstruct the ligand, let's say, and fix the periodic boundary condition of a ligand, but this can be anywhere in other periodic cell, not necessarily the one in which the protein is. So we have a special command to make sure of this, which is called wraparound. Once you've done this, you can align the protein, any part of the protein that you like. Here I suggested the residue 41 to 390, because we know they are a bit more stable. So we align this system to our reference, and in our reference, the lipid bilayer is plane parallel to XY. So once this is aligned with the fit to template option, we can calculate the position CV of the center of mass of the ligand, and let's say just the Z component of this position CV. So the procedure is this: we make the protein entire or whole. We make the ligand whole and in the same cell as the protein. Then we align the system to the template that I provided you, and then we calculate the position and the projection of the Z-axis. After this operation, this projection Z component of the position CV is a good measure of how far is the ligand from the membrane bilayer. So did you complete this? How many of you completed this exercise, which was pretty difficult? Nobody?
I think I managed to, but I'm not yet.
Okay. Other people?
I had problems with this group by option.
Okay.
Wrap around. In the manual, it's not really, at least it's not explained that well to me. That
okay.
I think in the manual, it's just there's an example and it just says free.
But it's not clear
what this free actually indexes.
And I would like to hear also from people that actually had problems, what are the main obstacles in this exercise? Don't be shy. Something that you really didn't, why you didn't manage to complete this exercise.
I couldn't figure out the RMSD from the last one, so I couldn't do this one also. So just connected.
Other reasons? I think if you in the future you would like to use Plume, this and understanding how to deal with PBCs and broken molecules and putting things in the right place, it's very important to avoid some serious mistakes. And so this is a very important exercise that maybe not now, but afterwards, by rewatching the YouTube video and redoing the exercise, I think you need to be able to do exercise 6 and 7 if you want to avoid mistakes in the future. So let me, so all these commands are doing some transformation of the coordinates of the system or the frames of your MD trajectory inside Plumed. So you want to check that they are doing what you expect, and there is a way to do, which is basically inside Plume to print out a new trajectory of a system after all these transformation are done. So this is, imagine we have understood how we have a solution for this that I will show you. Then you have a Plume input file, and to check that these transformations are actually what you expected, you can basically print out, after all your commands here, a new trajectory, which I call align.grow, and you can print out all the atoms or whatever you need, and to look at it and see that actually it is what you expect. So this is not only for this specific exercise, you can always do that and to check that you obtain what you expect. So now I will go from the solution and will explain a bit better what this group by is. So here we go. Exercise 6. Again, we create the directory and we go inside and we first activate this functionality, molinfo. Let me, because I don't remember the name of the, here we go, something like this. So the first thing, you want the protein to be not broken by PBC. And I'm using MD analysis syntax here, but now you know very well, to select just the atoms of a protein. The glycans are excluded. The reason is that the reason is that the glycan actually are defined after the end of the protein in the PDB, and all molecules rebuild the protein as a continuous and a whole by following the index number that you specified and assuming that these are kind of consecutive atoms. So you start from the first one, you put the second one in the same cell as the first one, and you grow your protein like this. Now, at a certain point, you arrive to residue 24, and you should grow, let's say, the glycan, but the glycan is not there because it's specified at the end of at the end of a protein. So that doesn't work very well to specify, let's say, a whole range in these all molecules that is not consecutive, let's say, in closed space. So what we do here is we reconstruct ligand and glycans, but afterwards, after we use these all molecules just on the protein, we fix the problem with the ligand and the glycans. So this is very specific because the glycans are defined at the end of our PDB file. So we make just the protein whole, and then we define a group, which is the ligand atoms with MD analysis. This is now is a group of atoms that we can reuse for many other things in the rest of the Plume input file. Now, what we do here is to put all the ligand atoms close to, let's say, the the disordered and terminal residue of the protein, because we know that the ligand is staying there. We actually restrain the ligand to visit this part of the conformational space above the upper lipid bilayer. So what we do is put all the ligand atoms in the same close by to this N-terminal part. The problem is that if the ligand is kind of a boundary of the cell, you might broke the ligand in different cell while finding the position which is closer to the N-terminus. So you want to make sure that all the atoms of this group ligand are in the same, let's say, simulation cell. They are not broken by PBCs. And at the same time, they are close and in the same cell, let's say, or neighboring one of this selection around. So to make sure that these atoms are not broken by PBC, you have to specify this group by option, and by group, if you put 26, because 26 are the number of atoms that compose the ligand. Okay, so basically the first atom of the ligand is put in as close as possible to the atoms of the specified here, and then the other atoms of the ligand are put in the same simulation cell, in the same periodic cell at the first one. So you have a guarantee that the ligand is not broken by PBC and as close as possible to the N-terminus, flexible N-terminus. Is this clearer now what is group by is? Bit better?
Apart from it just being the number of atoms in the group you're selecting, why would you have to explicitly define it then?
Because it happens that this wraparound can very well break the atoms that you specify in the atoms argument, unless you say this should be considered as one group of atoms.
Okay.
Imagine, for example, you want to. It not necessarily mean that it's always the same. Let's say the same. Total number of atoms that you have there. For example, sorry, I will make an example which is easier. If you want to print out all the water that is closer to certain residues and wrap around these residues, actually, so you can select some water molecules here, and then you want by atom indexes, so oxygen and hydrogens, and then you want to group these waters by free in order that every molecule, let's say, is not broken by PVC. So if you have different, let's say, molecules in these atoms list, in this case, you have one ligand and you want all of the atoms to be, let's say, not broken by PVC. Does it make more sense?
Yeah, I think I get now. Also, another question.
Yep.
Can you end up in a situation where so now you have 3 wraparound commands in a row, right?
Yes.
Can you end up in a situation where you break a molecule you already wrapped around in a previous, for example, number 3 breaks the molecule you wrapped
I don't know if you could, I don't think you can arrive at that. This is certainly not the case, because what I wrap around is things that have not been reconstructed here as a whole. So here I just work on the protein, and here I do ligand and glycan separately. It might happen, maybe. I don't know. I never thought about this. If you try to fix this PVC for the same set of atoms multiple times, what can happen?
Okay, thanks.
Other questions?
Sorry, in a system, for example, with water or membrane bilayer, for example, we had to add other wraparound in order to fix the PVC, or not?
It depends what you want to calculate. Here, for example, here is a membrane protein, but the lipid bilayer is not there. If you're asking yourself how many lipids are around certain residues, or you want to visualize them, yes, you can apply these also to lipids or to ions. If you want to print out the conformation for which the ion is close to a certain residue, yes, you have to wrap around also the ions. In this case, we just care about the ligand and the 2 glycans, which is a special case because they are defined in a weird place in the PDB file.
Thank you.
There are some other example in the wraparound manual page of the use of this keyword, if you're interested.
Maybe I have one last question also.
Sure.
So GROMACS, for example,
yeah,
a lot of tools to fix periodic boundary conditions also. Is it bad practice to use these, or is there any reason to use PLUMED over the two existing GROMACS, for example?
Very good point. In most cases, in simple cases, for example, you just have a protein, and it's one chain. All the tools of GROMACS, GMX, TRJ conv, minus PVC, blah blah blah, they work pretty well, and you don't need this. The only situation that might be a bit more trickier is exactly the ones in which you have, for example, multiple chains or ions around, or a ligand like this case. And then you might need a multiple combination of GMX, TRJ conv to get to the desired output. I think in my experience, maybe just me, but when you have multiple chains or ions and ligand that you want really to wrap in one simulation cell, it's a bit, you can do it with GRAMAX post-processing tool, but it takes a bit of playing between the option.
Thanks.
You're welcome.
Can I maybe add one more question to
Sure.
this?
Yes.
When you would use fit2 template during your simulation,
yep,
is there an advantage over using the fit2 template over GRAMAX COM mode, where you center your protein in the middle of the box and also try to remove rotation?
It gives you more flexibility because you can fit to anything that you have, to any structure that you have defined before, and so any reference system that you have defined before. Here is very specific because in membrane protein you want the lipid bilayer to be aligned, to be in a certain absolute position, let's say. So if you have a PDB that tells you this position, then you can align to this specific place. And also you can align again based on certain atoms and not others. So it's a bit more flexible, I think.
Okay, thank you.
You're welcome. So if there are no more questions, and I finish this exercise. So this part of is just to define the ligand and to make everything in one simulation cell, let's say. And once this is done, we have to fit to one conformation, and we can reuse the one we used before, which is alignment of the, let's say, the stable atoms, which, if I remember correctly, is this PDB here. Once we have done this, basically we can define the center, a geometric center of the ligand, and take as collective variable the position. At this point, we don't need no PBC means I've dealt with the periodic boundary condition before. Do not do anything, just to be sure that all that you have done here is not screwed somehow by some PBC check and fixing inside the collective variable. And I told you, as I told you, you can control that this is done as you expected by printing out all the atoms in a new trajectory file after alignment. Okay, it is important to notice one thing. In the fit template, you are using certain atoms for the alignment, just the backbone of residue 41, blah, 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 but actually to fit. But actually, once you have defined with this optimal alignment, the transformation is applied to all the atoms here that PLUMED is dealing with. So you are fit to template. We are moving and rotating and translating all the atoms here. So you will notice when I print out all the atoms in the trajectory file, you can see that all of them are correctly positioned. So let me run this. Hopefully I didn't do any mistake. So this will take a little bit of time. And then we will manually, okay, this is done. So the first thing I want to check, this is exercise 6. So we go into exercise 6 here. So we'll have now the Plume input file and the new trajectory file. There's something missing also. Okay, so I forgot to print out the Colvar file. So what we want, in the end, what we wanted is the Z component of the position. So I forgot this line, so but never mind. So let's rerun. In the meantime, probably. Okay, let's wait a second. Okay, and this is finished. Now I have a Colvar file and also this trajectory file, which I'll try to open. Let's see if it's clear or not. It might take some time. Perfect. So on top of this, I want to visualize also the starting PDB. Okay. So as you see, if you're familiar with membrane proteins, you see that this is a membrane protein pretty quickly because you have this alpha helix part. And I try to put in red. This is the starting PDB file. Okay. And the membrane is parallel to the XY plane. So this is basically the transmembrane part. Let me make this bigger. Okay, so this is the starting PDB file. And this is the trajectory after plumed alignment, which I will put in this color, for example. So the alignment should be better in the beginning, probably, but not really. Probably is not the starting conformation of MD. Anyway, the system that was before broken by periodic boundary condition and is made and moving around, translating in different cells, is aligned decently well. The problem, I can tell you what it is, decently well to the initial PDB. So the problem is not perfect because there is not one part of a protein here which is pretty mobile. So it was better maybe to align just not on residue 41 to 390s, but to a subset which is actually not moving. So the actual transmembrane part and not this domain here. But anyway, Plume did what we told him to do. And we can have a look at the other part, which are the glycan. So the glycan are not a protein and not a ligand. And we can plot with van der Waals here, for example, in red. So these are the glycan that are attached to the N-terminus. And this should be always not broken by PBC and let's say in the same box as the N-terminus, which seems to be the case. You can have a quick look. And you should trust me. And then the ligand, we can make it yellow. Okay. Same thing with the ligand. So it will be put in the same simulation cell, which is pretty big, but it's in the right position. No, here it's inside. So it seems that the transformation that we are doing are correct. Now we go back to the notebook because we calculate after this alignment the Z position of the small molecule. And if you did things correctly, it should go from 8 more or less to 18. So people who completed this exercise is what you saw also?
Yes, for me this is what I also saw.
Yes, me too.
Perfect. Perfect. Good. Now, I think we have 15 more minutes, and in the last 15 minutes, we go to exercise 7, which is estimating binding propensity. So this is, does any of you completed this exercise or nobody at all?
I made an attempt using Python scripts, but I don't know if that was the proposed solution or not.
What do you mean, Python script and not Plume for post-processing?
Yeah, I used Python to write like a long Plumed file.
Yep.
And then I used also again Python to analyze, so I then used the large Plumed file to generate the frames in GROW files for each residue number.
Okay.
And then I used Python also to analyze those GROW files.
Okay.
I don't know if that was the solution we should take.
Close. I think it's close. There are some things that you could have done in Plumed, but others are better done in Python, like creating a Plumed input file, for example, a very long Plumed input file. Other solutions? Nobody? Okay, it was complicated, but not impossible. So what we want to compute is the number of conformation in which the ligand is bound to again, this N-terminal part of the receptor. And when I say bound, it means arbitrarily that there is at least a pair of atoms which is closer than 4 angstrom. Atom of the ligand and of the protein or residue of glycan that is closer than 4 angstrom. This is a bound conformation. So we want the number of bound conformation, but also we want this to be defined at the residue level. So we want to see if there are hotspots on the sequence in which the serotonin want to bind more than other residue or other glycan. So we want a profile, a binding profile per residue. And then we also want to isolate all the conformation and write all the conformation that are bound in a separate GROMACS file after fixing all the PBC as we've done before, so we can look at them and check that they are right. And that's it. So I will show you how to do it, and the easiest way to do is to create a Plumed input file. This time is in Python, because there are some loops that we can do in Python, and these are easy to do in this way rather than Bash as we did before. So we copy many things that we use in the previous exercise because we want the system to be not broken by PBC and very nicely in one simulation cell, because we want to print out some conformation. So we want it nice. So we do exactly what we did before. We fix the PBC of the protein, then we define the ligand. Here I'm defining groups for other part of the protein, for the ligand, for the N-terminus, so the residue 140, and for the glycans. I define this group because we will use them multiple times in the rest of the Plume input file. So it's convenient if you use this range multiple times just to define one and give a name. Glycan N24, glycan N32. And then again, we do what we did before. We wrap the ligand around the N-terminus, and we wrap the glycans around the corresponding residue here. And we fit the conformation to the template. So this is more or less the same input file as we did before. Then now starts the actual calculation of the bound conformation. So what we need first to check if overall is bound, the ligand is bound to the protein, we calculate the minimum distance between the atoms of the ligand and all the atoms of the N-terminus and the two glycans. And this can be done using the distances collective variable. This is a special collective variable. It's called a multicolvar. It actually calculates more than one collective variable and then gives you some properties of this set of collective variables. For example, in this case, it will distances. We calculate all the distances between the ligand atoms and all of these atoms. So it's a lot of distances. And then it will take the minimum. Here, if you look at the instruction and the manual for distances, you will see that the minimum is actually a continuous function, because this is what we need for a non-sampling simulation, but it doesn't really matter for us. Imagine it's just the minimum distance between these two groups of atoms. And this, of course, if this minimum distance is lower than 4 angstrom, we can define the system as bound, the ligand as bound. Now we do exactly the same thing, but here it will be ligand and the atoms of specific residues. So we cycle over all the residues in Python. That's why Python is useful here. And we print out the distances between the ligand, and now the second group is just specific residue. And that's it. So this is done basically 40 times. And then we print out the distances to the glycan, ligand and glycan. That's it. So now we have 40, 41, 33 collective variables that are written automatically by Python in a Plumed input file. Now, what we also want to do is to print out conformations if some criteria are met. And to do this in Plume, you can use this special keyword, which is called update if. So you can tell Plume to do whatever you like, only if some conditions are met. So in this case, we want to print out the atoms on different files if the corresponding minimum distance is lower than a certain threshold. So now here we cycle over the 40 residue plus, let's say, the global distance of a ligand to all these groups. And we print out on this file separately all the atoms of the system if this distance is lower than 0.4 nanometer. And we do the same with the glycan. So at the end of the day, we will have 43 files with the conformation bound to certain specific residues or specific glycans or overall. And this loop is done in Python. Finally, you print out also the value of the collective variable that you're using. So this is a bit elaborate, and you use Python to create a long plumed input file, but it works pretty nicely, and I will do this part also. Okay, so this should be fast because it's just creating a plumed input file, and let's exit here. So we're exercise 7. So now, thanks to this Python script, we have prepared this long plume input file, which would be boring to create by hand, in which you have a lot of collective variable, one per residue, one per glycan, and then you have a printout of the conformation if these distances met are lower than 4 angstrom, and you have many of them. And in the end, you print many Colvar files. So this is really 332 lines of plume input file, but you didn't have to write all by hand. So now the plume input file is done. We just run this driver again, and we wait. So is this what you did, more or less, to create the input file with Python?
More or less, but I used coordination instead of distances, and then
Perfect.
not using a multi-Colvar, just a regular.
Okay, that can be done also with coordination. Perfect. So this will take a while because I can show you it's writing a lot of Colvar file and a lot of Grow file. So now I don't want to make this longer than expected, but if you repeat this at home and you check this trajectory file, for example, you check VMD bound R glycan 2, that should be all the conformation with nice PVC fixed and so on and so forth of just the bound conformation to the second glycan, which let's see if I can do it quickly. This will be a yellow. Sorry. Yeah, almost done. Huh? Okay. So this is the ligand, and this is and these are the two glycans. Okay. So if you look at this file, it should contain all the conformation in which the ligand is bound to the second glycan, if I did this correctly. Yes. Now, what I ask you, apart from writing down this conformation, is to quantify how many bound conformation and the profile per residue and per glycan. So this is pretty easy because now you can look at the Colvar file, analyze the Colvar file, and count. And what I prepared here is a quick way to do it. So basically, now you have 43 Colvar file. The first one, R0, is the minimum overall distance. So you can read this and count how many are lower than 0.4. And we append to a Python list. Then the other in this cycle from 1 to 40 are the distances at residue specific distances. So we do this, we count how many conformation are bound to specific residues. Then we have two Colvar files for the glycans, which I call them differently. So I don't know why. So I will cycle over these two glycan Colver file and do the same. At the end of the day, I have a Python list with 43 entries. The first one is the overall bound conformation. Then I have 40 bound conformation per residue and the two glycans at the end. Now, what I'm doing, I'm just renormalizing the overall number of bound conformation with, let's say, the length of the trajectory. And at the residue level, at the glycan level, I'm normalizing by the number of bound conformation. So it will be relative to the total number of bound conformation, how many conformation are bound to residue 2 or 3 or to the glycans. And then if I do this, I can plot a nice bar plot in which I color differently the overall amount of bound conformation, the one per residue and per glycans. So you can have a look if you don't trust me. And at the end, I can plot something like this, which is the profile. So this is overall 10% of a conformation. The ligand is bound somewhere. And if we analyze this bound conformation, I have a profile per residue that tells you where it's binding the ligand. And if you can see, it's binding mostly to the two glycans. So the people who completed the exercise, did you get something similar or not?
No, I did something wrong with the glycans, I think, but I did that in a separate Plume file because those are much lower with me, so something went wrong. So
okay.
I did something wrong there.
But the profile on the protein side, this red one is similar. So it's mostly
similar,
in the
but not really the exactly same values. But that's maybe because I counted, a bit differently with coordination or so. I don't know if that's
okay. It might be possible. Yes. So other people who solve this exercise? Nobody. Well, I think this was a kind of challenging exercise, but I will let's say add to the repository, to our GitHub repository, the spreadsheet, the notebook, so you can, if you want, go through the solution and learn how to do this more complicated alignment to template and fixing of the PBCs. So you can take your time, and when you want or when you need, you will have a reference solution. So I think we have been very long. It's 2 hours. So do you have final question regarding these exercises or general question before we go? Any of you? No other questions? Okay. I don't know if Giovanni is still there. Probably not. Okay. So I think we are done for this for the class. Please, if you have problems, you can in the next few days, and you want to ask questions, I'm always available by mail. Otherwise, I think we can finish here. Okay. Well, thanks for attending these 2 classes. I don't know if we will meet each other for the future one, and otherwise, good luck for your research, and have a nice day.
Thank you so much.
Thanks.
You're welcome.
Thank you.